All right, in this video, we're going to talk a little bit about limits of sequences. And as I mentioned in a previous video, at a first glance, it seems like this should be a little bit different than what you've seen thus far. Because if you take the limit as x goes to infinity of 1 over x, we know that 1 over x you can think of as a function that takes in a continuous set of values, x, and so x could be 5, but it could also be 5.103. It can take on any decimal number. And so it makes sense to think about how x approaches infinity as just x growing in this gradual way. But when we talk about sequences, we're limited to integer values for the inputs. And so we can talk about sequences like 1 over n, but n only changes by integer amount. So it can be 2, 3, 4, 5, but it can never be 5.5. So how do you define a limit in the context of a sequence? Well, the rigorous definition is something like this. We say that the limit as n goes to infinity of an is equal to L. So we're saying that a limit of a sequence exists, and it's a number L, if given epsilon greater than 0, there exists an n such that for n greater than big N, the difference between an and L is less than epsilon. All right, so if you took Calc 1 with me, this may look a little bit familiar. We've got some epsilons floating around, and it looks like a little bit of a mysterious statement. But let's see if we can understand what that means. So when we say that a limit exists, what we're first saying is that there is some number that the terms in the sequence are getting closer to. So L is what we're using here to represent the limit of the sequence. And when we say we're getting closer, what we mean is that the difference between an and L is getting close to 0. So this distance, an minus L, and we put absolute values there so that whether an is bigger than L or less than L, but we get positive numbers either way. So this is the distance, and it gets small. And, well, just saying that it gets small is really not very precise. You have to clarify, what do you mean by small? And so in the definition we say is that given epsilon greater than 0, meaning given any definition of small, eventually the terms are going to be sufficiently close. So this difference has got to be less than epsilon no matter what epsilon anyone could choose. All right, so if epsilon is 0.1, we can say yes, eventually the terms in the sequence get within 0.1 of the limiting value. If epsilon is 0.01, then we can say that eventually, yes, they're going to get within 0.01. In fact, they have to be able to get as close as you could possibly want. Now, it is not true that all the terms in the sequence have to be that close all the time. That's where this n part comes in. It says there exists an n such that for n greater than n, the terms are close. That means if we go out far enough in our sequence, then we would see that all of the terms in the sequence will be sufficiently close. All right, so let's look at an example of this. So here's a little Desmos animation. Here the blue dots represent the values of the sequence, and the function I'm using here is f of x is equal to negative 0.8x, negative 0.8 to the x. And you'll notice that if you just plug in integer values for x, this is a sequence that bounces around back and forth. So it starts out at a value of negative 0.8, that's the first dot, and then it goes up to positive somewhere around 0.65, and then it goes down, up, out, down, up, and it bounces back and forth. Now, if you look at those blue dots, as n grows, so meaning as we move along the x-axis, you'll see that the terms seem to be getting closer and closer to some value. In fact, I'm betting you can guess what that is. It looks like they're getting closer and closer to 0. So, is it true? Is that true? Is it true to say that the limit of the sequence negative 0.8 to the n is actually 0? Well, what that would mean is that given a value of epsilon, or giving a size of a target around 0, all of the terms in the sequence will eventually be within that target range. So here I've got a variable k. I couldn't use the variable epsilon in this particular calculator, but think of k as epsilon. That determines the size of the target, so we can make that bigger or smaller. And the question is, do the terms in the sequence eventually all get within 0.2 of 0? Well, you can see that yes, it looks like once we get past 1, 2, 3, 4, 5, 6, 7, once we get to the 8th term, all of the blue dots are within the red band. And if we make the target smaller, we'd see that we have to go a little further in our sequence. But again, eventually, all of the blue dots are within the red band. And if we can do that, no matter how small the target region is, then it makes sense to say that the limit actually exists. All right, so that is the precise definition of the limit of a sequence. But the good news is that there's actually a theorem that can allow us to compute these sequences without having to resort to epsilons every time. And this is what's called Theorem 1 in your book. This is from chapter 10.1. It says the following, that if the limit as x goes to infinity of f of x is L, meaning this is a regular function, we're not talking about sequences right now, and an is equal to f of n, which means that f of n is the function that we could use to calculate terms in the sequence, meaning at integer values, it gives you the terms in the sequence. Then the limit as x goes to infinity of f of x is equal to the limit as n goes to infinity of an, which is equal to L. Okay, so what does this mean for us? Well, it means that when we want to take the limit of a sequence, if we have a function whose values match the terms in the sequence at the integers, then we can use all of those old limit techniques to solve that limit and proceed with confidence that the sequence is going to approach the same values as the function. As x goes to infinity, we can find out what f of x approaches, and that's got to be what an is also going to approach. All right, so this may not seem entirely obvious, but it's a really important result because it means that we don't have to worry about this distinction that sequences only take on integer values. We can actually use all of our old limit techniques, the limit laws, we can use L'Hopital's rule, we can use any of those techniques to help us find limits of sequences as long as we can actually write down a function to compute the values of the terms within the sequence. All right.